In the last video, we looked at truth tables, which is the method we use to clearly show the output for different combinations of inputs of different logic configurations. We've already learned about the three main gates, and today we are going to look at combining them into circuits as well as applying our knowledge of truth tables to these circuits. Here is a recap of the different gates we will be using and their respective truth tables. We will be using these a lot over the next few slides. So far, we've looked at each logic gate individually, but they are of most use within computer science when they are put together to form Boolean logic circuits. We can represent these circuits with diagrams. For example, we could have a circuit that includes an AND gate, and also a NOT gate, and then the outputs of these gates could then go in to an OR gate. This is one simple way that we can combine some gates together. There are many more different, more trying ways to do this, and there are a lot of different mathematical configurations that you will get to later on in your computer science journey. Although showing a visual representation of a logic circuit is great, it's important to know how to represent them in writing, as if you take this subject beyond the GCSE, you will find that there are a lot of mathematical uses for Boolean logic, and written form is the way that this is done. Although there are a lot of different notations used for Boolean logic operators, such as a dot for AND and a plus sign for OR, and while the OCR exam board accepts a few different ones in the exam, and your school might have taught you a different one, it's key to note that for your exam, simply writing the words AND, OR, and NOT will be fine. Therefore, to keep it simple, that's exactly what I'm going to show you in this video. If we take our circuit from the previous slide, we want to represent this in a way that can simply be read, and that further logical processes can be carried out on. Therefore, we are going to want to create what we call a logical expression. If we were to say that the three inputs we have are called A, B, and C, and our output coming from the OR gate on the right hand side is labelled Q. Now, with logical expressions, we always set it out, so it is the output equals. So we'll have Q equals. Now, the best way to work with logical expressions and circuit diagrams is to move from right to left on the diagram. So we'll start off with our, what I like to call the terminal gate, and here we have our OR gate. So what we can decipher from this, because it has two inputs coming into it, it will be the central operator of our expression. A key thing to note here is that if this gate is a NOT gate, we know that there's going to be a NOT operation around the whole expression. So therefore it would be Q equals NOT and then everything else. But because this isn't an OR gate, therefore this will be pretty much central to the expression. The next thing we need to do is identify the inputs for this central operator. So if we look here, we know we've got an input coming from here and an input coming from here. So we'll start with this top input here, and we can see that it's actually the output of a gate. Now this gate is an AND gate taking in inputs A and B. So what we can say is that this input is actually going to be A and B. Then we look at our next input, come across here, and we see we have a NOT gate, so it's the output of a NOT gate, and this NOT gate has the input C going into it, so therefore we can say that this input is actually not C. So therefore we have the inputs of A and B and not C going into an OR gate. So the way we're going to write this is A and B we're going to put this in brackets because we're going to put the or here, and it just means we're not seeing this, although with the laws of Boolean algebra, which is a topic you will get onto in the A level if you decide to take it, and comes before or, it's kind of like bid maths in maths. So to make it clearer to ourselves here, we're just going to put brackets around A and B so we know that the B isn't operating with the or. It just makes it clearer to us. And then we will put not C on this side. So therefore, that is actually our full expression. Q equals A and B in brackets or not C. And there you can see in neater writing, because the computer isn't left-handed like myself, Q equals A and B or not C. Now it's time to bring in the skill that we learned in the last video, and that was use of truth tables. We need to show the outputs for all possible combinations of inputs for our circuit. This is the final layout of the truth table in terms of rows and columns. However, for practice, we're actually going to add in an extra 2 columns, which are the outputs of A and B and not C, and then we can easily OR these together from the table. It makes it more visual for us, and we're not having to do too much in our heads. So as we did in the last video, we looked at all of the different possible inputs that we had, and for a 3-input circuit, these will be as follows in no particular order. So we could have all 3 as 1s, but we could also have all 3 as 0s. Okay, we could have A being a 1 and B and C being 0. We could have A being 0, B being a 1, C being 0. We could have A and B both being 0, C being 1. We could then have A and B being 1 and C being 0. We could then have A being 0, B and C being 1, and then finally we could have A being 1, B being 0, and C being 1. Now it's time to look at the next 2 columns, and this should be pretty simple for us as we have actually already really done these truth tables, because it's actually just a case of having the truth table for an AND gate and the truth table for a NOT gate. However, with the NOT gate, we'll be repeating it quite a few times as well as the AND gate. We're just repeating it quite a lot, but it just makes it more visual and easier for us to get our Q values in the end. So we'll go row by row, but we'll look at the A and B column first. Now, we know that A and B will only output 1 if A and B are both 1. So therefore, we can take a bit of a shortcut here and look at our table and think which rows have A and B both being 1. Now, the answer to that is this one here, and then this one here. The rest of our rows don't have both A and B values as 1, so therefore the rest of them will actually be filled in with zeros. Again, if you don't get that concept, go back to the last video and you should remember things and then look back at this video and think, oh yeah, I see what he's done there, because again, it's a simple concept, but it's just one that needs to be drilled into your head. Then we look at our not C column, and we basically just go into the C column and invert everything across. So on the first row, our C is 1, so that will be 0. On the second row, our C is 0, so that will be 1. On the third row is 0, so 1. On the fourth row, it's 0, so 1. On the fifth row, it's 1, so it's 0. On the sixth row, it's 0, so we have a 1 again. And then on the seventh row is 1, so we have a 0. And on the eighth and final row, we have a 1, so we have a 0 for not C. Now we can get to the final output, which is what we want. We're looking for our Q column now, which is the OR operation on these two terms here, A and B and not C. So we look across and we say 1 or 0 is 1, 0 or 1 is 1, 0 or 1 again is 1, 0 or 1 again is 1, 0 or 0 again, not again, sorry, is 0, 1 or 1 is 1, 0 or 0 is 0, 0 or 0 again is 0. Now, with truth tables, although this may not be GCSE, but people do often draw conclusions about a circuit from truth tables. So for example, although it's not a very useful conclusion that we can draw, we can say that if ever the input of C is a 0, Q will always be 1, because if C is 0, we're inverting it, that will change to a 1. We're always putting a 1 into our OR gate here, so therefore, if we have a 0 for C, we will always have 1 for Q, because the OR gate will always have a 1 inputted into it. These are just little conclusions that you can draw. So whenever you're doing a truth table and you know you want to take this beyond the GCSE, try and draw some conclusions. It's good practice to get into, and it's a good way to impress your classmates once you get into sixth form. And I'll always do this just to save you from my left-handed writing. Here is a neat typed version of the filled out truth table. So, we've gone from a diagram to an expression. So, let's go from an expression to a diagram. So, here we have the expression Q equals not A and B in brackets and C or D in brackets. Now, brackets are a difficult concept within Boolean logic. Sometimes they're needed, sometimes they're not. I put them in because ultimately, although they might not be needed, they're nicer for me and I get to see it. However, here, there is one set of brackets which is quite important. So, firstly, in the exam, you can always get guaranteed marks on these types of questions by showing the inputs. So we can look and see what our inputs are straight away. And we know that they are A, B, C, and D. So, obviously, I've shown you the circuit diagrams before. And on those diagrams, we had our inputs listed down the left-hand side. So that's exactly what we do. Now, when I was doing my GCSE, I was told that that would always get you at least a mark. I would still assume it would, because it's a good thing to pick out and it's a good starting point, and you should be given credit for that. So now we've identified our inputs and we want to know how these inputs are interacting with each other and which inputs directly interact with each other. So we look at this here, we can see that A and B are interacting with each other within an AND gate. However, as you can see, these are within the brackets next to a not. Therefore, that means that actually the output of this A and B will be then run through a NOT gate to invert the output. So, we take our inputs A and B, we pop them into an AND gate. Then, immediately coming from there, we pop them through a NOT gate. So that's this half of the expression done. Now we want to look at the other half. Find our inputs. As you can see, we've still got C and D to sort out. As you can see, it's pretty simple here. They are just put through an OR gate, so therefore we can draw that on pretty simply. Okay, So now we want to see what's left. We have an and in the middle here. Now if you notice, either side of this and we have our C or D calculation, which we've got down here, our not A and B calculation, which again we have here. Okay, so what this means is that actually these two outputs are going to be the inputs for an AND gate here. And then that gives us our output Q. These problems are all about breaking it down and making sure that we catch every piece of information at the right time. Because if we miss a not, we miss an and, we miss an or, going back is a little bit difficult, especially if we forget a pencil in the exam. So we really want to think it through first and make sure that we know that this is the right thing to do. Again, it's always best to practice and practice and practice. There are plenty of past papers out there, plenty of specimen questions, and always ask your teachers for help when you need it. So as you can see in the nice big writing on your screen, that is the end of our coverage of the topic of Boolean logic. It's a great, fun, important topic in computer science, and is certainly a great way to pick up some easy marks in the exam. Our next topic is going to be units, where we will be going over the different units of measurement for data capacity and data storage. It'll be our first topic that we're actually going to cover from paper 1 of the GCSE. This topic has been from paper 2. As ever, if you have any questions on anything covered in this video, please feel free to comment down below and I will try to get back to you as soon as I possibly can. And once again, don't hesitate to ask your computer science teacher about anything you don't understand, as they will be the most reliable source of information.